I start with a short definition. This one, there are several ones you find in different books and different occasions. Basically, basin modeling refers to the simulation of the thermal history of a basin for a given geological depositional history associated with it, the time and volume of hydrocarbon generation, as well as migration accumulation. That already points in the direction where the whole topic is coming from. It's coming from hydrocarbon exploration. People wanted to know whether they can basically predict the timing of hydrocarbon generation, migration and accumulation. So they have an additional tool to focus their quite expensive exploration to more successful locations. Okay, and we have something here, escape. Okay. I don't go into all details, but you can do basin modeling in one dimension using a well location, really drilled well, or you can construct your own well from surface data and look at the thermal evolution, depositional history, model maturation of the organic material, and basically use this to get a timeline on your one sample location, how it evolved through time. Because basin modeling will always force you to develop a continuous history through which it was deposited, uplifted, eroded, and so on. We come to it in a little bit more detail later. Okay. That's quite interesting. You can do this in 2D if you have a seismic profile. If you construct in tectonics, if you construct a profile which you balance through time, you could use that for basin modeling. This is now just 2D model somewhere from the North Sea where they studied hydrocarbon generation and migration. The red color indicating the formation of gas, green the formation of oil. The arrows are just indicating the direction and a little bit the magnitude of hydrocarbon migration. I hope we don't have any people who are red-green blind, because unfortunately in hydrocarbon exploration they choose red for gas and green for oil, and people who are red-green blind, it's all gray. But okay, this will have probably, oh, escape. Yeah. Sorry about this. And you can do the same thing in 3D. So look at the whole basin, part of the basin, how it evolves through time. Most simple, obviously, is the 1D, because you don't need so much data. 3D is something you usually can only do if you have either an enormous amount of well data, trying to construct a model from that, or better so if you have seismic to work with. Without seismic, it's usually quite difficult to get a reasonable model. For those who are actually interested in working in this field, there are several packages. Put them basically in the order where they appear or how often they are used. Petromod at the moment, it got bought by Schlumberger a few years ago, so it is at the moment the most common and standard being used in oil industry. TMS-Flow is the French counterpart, developed by the IFP-EN now. IFP Nouvelle Énergie, or Énergie Nouvelle, in Paris. Permedia is something which was a little company in Canada, and it got bought. Can we stop this somehow? This is getting a little bit annoying. Bought by Halliburton just also a few years ago. So basically all the packages are now in the hand of big companies. There are smaller, more simple packages like Trinity, and should be Genesis and not Genesis. Basin Mod is an older 2D model from a service company, River Plate or Plate River Associate. And Nova is a relatively new 1D model by a company called Cyrus Exploration. They're not just names, not so important, but sometimes you hear them. So basin modeling tries to reconstruct the basin evolution through time. For sedimentary basin, that is the main focus, because in sedimentary basins you find hydrocarbons. That's the reason why it was developed. You look at the burial history of the basin. From the burial history, you model the thermal history, and when you get all these things relatively correct, hopefully, you can look at hydrocarbon generation, migration, accumulation, things like this. Certainly, they're broken down now as 3 steps. You don't do this in 3 steps. They're calculated simultaneously, and they're interacting. Burial history. Burial history is basically the evolution, the deposition and burial of sediments, periods of non-deposition, like in Argentina, we have very old sediments in the Chaco-Paraná basin, and then there's a long gap, either nothing has happened or eroded, and then deposition took place again. You can also integrate deformation to a certain degree, but not directly in most of the packages at the moment, but you need special programs to work from the tectonic side, and then you can, in the next step, you can put these things together. That's why I put deformation really in brackets, because the current packages all basically run without any deformation. You look at try to reconstruct sedimentation rate. You look at the environment, the facies, the organic matter accumulation, basically to, at the end, come to a conclusive model how hydrocarbons were generated and how they could migrate. You can also look at, or you need input from paleogeography, paleobathymetry, paleoclimate to correctly reconstruct the entire geological history. You need rock properties to reconstruct your basin, because sediments compact, porosity is reduced, permeability changes, the density changes. With all these things, also the thermal properties change, conductivity, heat capacity, and so on. So these things are essential later on for setting up the model. If you're looking at hydrocarbon generation migration, you will then look at hydrodynamics. In the model here, it is not what people from groundwater hydrology are looking at, thermal convection and so on. This is something which is too small of a process to be included in these models. They don't do this. They only do one thing. They calculate how much water can escape from the compacting sediments, and if they cannot escape because there's a seal on top of a porous sediment which can compact, they will calculate the pressure and over time the release of the water from these layers. So a small amount of hydrodynamics is really included, but not what you see in groundwater modeling software like here the VASI thing people use here, FEFLO, that's the name, or other groundwater hydrology programs. That's something which is not included here. Then you can construct such nice burial histories. On the horizontal, on the x-axis is age, how it evolves through time. Vertical is basically burial, is depth over time. And the colors, we can choose, in this case, it's temperature history, or temperature, how it evolved through time. And then on the other side, I think it's porosity, not well to be read. So you see that, that the warm colors indicate always large numbers. So on top you have high porosity, and the deeper you get, the lower the porosity gets due to compaction. But you can also display all kind of other things. They calculate a lot of things, and you can have a look at all the variables which are available. For us at the moment, not so important. When you get the burial history, more or less correct, you can look at the thermal history, which also depends on the basin type, on the thermal events, whether you had a heat flow event due to seafloor spreading maybe, or some kind of volcanic event, or maybe nothing, or whatever. You can, the model usually, or the main process for heat transport, heat transfer, is conduction, these models. They don't really calculate advective fluid flow of water in these packages. Again, that is mainly a problem of resolution, the size of the models, the size of the elements. Could be done, but too time consuming. They calculate compaction, overpressure, because overpressure usually has an effect on thermal conductivity, besides on the pressure itself. And the pore filling is important because if you put a gas as a filling in the pore volume, it is a nice insulator. And I think I have some, no, I threw them out. So minerals have a high conductivity in general. Some have a higher, some have a lower conductivity. That changes. Pore volume, water has relatively low conductivity. So the average conductivity of the lithology depends on the amount of porosity and solid matrix. And porosity can be either filled, oil-filled, gas-filled, or water-filled, and then depending on the filling, it will increase or reduce thermal conductivity. But the details would be, or are, topic of a separate lecture. I'm not going to give here. If you're working in hydrocarbon exploration, you're interested how much oil is formed over time. So the model can then calculate, based on the hydrocarbon kinetics, how much, when and how much hydrocarbons are formed, whether they are expelled and where they're moving to. So pathway, migration of primary and secondary migration are topics of these models. In detail, if you have a good kinetic database, you can also then predict the density, API gravities of the hydrocarbons, viscosity, and so on. So all these packages, which are quite expensive to buy, unfortunately, provide you with a lot of data, which is important, especially for hydrocarbon exploration. It is not such a big topic for us, certainly not, but the potential is available. And yeah, you can also look at the trap formation and basically the persistence of the trap, how long are hydrocarbons being trapped and whether they can migrate through the seal at some point, break through the seal. So what kind of data you usually need to set up a model? Usually you need formation tops from wells, you need reports, logs and so on, so you can define the lithology, the boundaries between the different lithologies, the ages and so on. So this would be one type of basically one-dimensional data. Hopefully you have, if you work on a larger scale in a basin, you have seismic data interpreted, depth converted. We don't need time sections, they are not very helpful. You need them depth converted. So you can interpret the horizons, which don't necessarily have to be the formation tops. Can be, but don't have to be. And from this data, you can start to work to develop your model. I subdivided it still a little bit to get more feeling for that thing. You have geophysical data from seismics and well log data, which you then need later to either define your lithologies and their thermal properties and compaction behavior, and also you need temperature later on or other data to calibrate your model. We come to this at the very end. There would be temperature, borehole data, spontaneous logs, resistivity log, drill stem tests, whatsoever. All this data can be useful to construct your model. From the geological side, you need chronology of the different horizons. Some kind of stratigraphy is necessary. It sounds quite obvious, but as soon as you get in an area which is underexplored, this is getting a real hassle to define. You need the lithologies because you need to describe or define how your model will compact and conduct temperature. And really, very important, the last point, you need calibration data, because otherwise you can model everything, because you don't know in which direction your model might be correct or incorrect. Again, coming back, hydrocarbon exploration, it's our topic. You need to know which kind of kerogen type you have. I don't know whether you know. I hope you know what kerogen is. Most people do? No? Okay, it's the organic matter which is deposited together with the sediment and from which then later on hydrocarbons are generated. There are three different kinds. Kerogen type 1, 2 and 3, that is relatively simple. One is really the fat material which is very hydrogen rich, mainly derived from bacteria, algae and so on. Kerogen type 2 is the so-called most common one, has a stronger influence of material which is more persistent, so less hydrogen involved, but more oxygen and other material, also marine derived material. And then kerogen type 3 is material derived from land plants, much richer in carbon, much less hydrogen, and also more resistant against oxidation and destruction by by bacteria, because the plants itself already have to protect them against the organism trying to attack them on land. So the material has more rings, benzol rings and so on, so it is more resistant against bacterial access. But it is also material which produces less hydrocarbons because you have less hydrogen in the system. The typical oil, so kerogen type 3 is a gas-prone source rock at the end. Kerogen type 2 is an oil-prone source rock, and kerogen type 1, which is not very common, would be an ideal oil source rock. You need to measure how much Sea Org, how much carbon is in your system. You need to determine hydrogen index and so on, because with all this data you can later use the hydrogen carbon kinetics modules to calculate how much hydrocarbons form and how rich your source rock is and how many hydrocarbons are generated and move through the system. And I need my glass of water quickly. Left it here. So for us, or for general application, the nice thing about these base modeling tools is that they require a continuous timeline. So there may be no gaps. You must fill all your gaps which are in the depositional history of your sediments you're looking at, or your rocks you're looking at. So at some point you have to fill all the gaps. At the beginning, this is relatively simple. You just assume nothing has happened. And that's basically because it is not a very straightforward process, which also changes over time. The longer you're working with your model, usually you discover points which you may have overlooked at the beginning. They develop this concept of a conceptual model. So you develop a model which you assume correctly describes the geological history of your basin you're looking at, of your rock sequence you're looking at. In 3D, you need to describe the geometry of your basin. Present day is still relatively simple because you have the data. Through time, it's getting more interesting because water depth and things like this can be quite challenging to reconstruct. You need to define stratigraphy, chronology, because you need to know when something has been deposited, when it has been eroded again, redeposited, and so on. You need to also look at the post-depositional processes like timing of hydrocarbon generation through time, kinetics, and so on. And you need to define your the best calibration data to obtain to answer your questions at the end. So in 2D, hopefully you have some kind of nice profiles. We are still waiting for material from YPF to work on. So as much as I know, the treaties or contracts are not signed yet. Hope it will change. So that is something you might have. Several interpreted horizon, salt dye appear. At this profile, they forgot to clearly state whether it's time section or a depth section. At the end, you will come up with a model something like this. Looks a little bit different, but in general, you also have the salt dye appear here. You have the different horizons. They marked a few faults in the system here. The faults for these models are a problem because you cannot change the length. So at the end, this will produce a little bit funnier results. But this would be a nice conceptual model saying, okay, we deposited something, we have the movement of the salt at some point. It has to cut through different horizons. And in the next step, you would need to discretize it. And that's already a step where you lose, again, information, because you have to put a relatively strict grid over these things, and depending, you can make the grid very nice and narrow, but that means you need a lot of time to calculate because you have many millions of grid points perhaps, or you make them coarser and then you just lose a certain amount of information. But discretization is necessary because the models are numerical models and they are quite strict about what they use. Once more, geological profile, that's something which was drawn based on the seismic line, and that was then the interpretation or the transfer into geological model in Petromod. If here what they call the basement, because they have little information, you have the few graben structures and you have the different horizons through time. You can look at the whole thing now also differently as a time section, which shows when something was deposited of this layer. And you see that in this area, nothing was deposited of this layer. So something either has happened, it was eroded, or maybe nothing was deposited. And in this, since it's a graben structure, one has to look very carefully at all the different horizons, whether they were deposited when the graben were formed, or whether they were deposited or just dropped down when the graben formed. That's something you have to decide then and integrate it in your model. This is now just a different representation. They now colored it according to whether it is a source rock, reservoir rock, or just overburden, so on. But with that, you will put this in a model, run it, see how it, what the results are, go back, start once more again. For that, I will show you later in case study we have done here. Before you can run such a model, you need to define some boundary conditions. So what happened on the surface through time? What were the temperatures? So for that, unfortunately, they provide a relatively nice tool which somebody has constructed. You can define temperature evolutions through time. The bigger problem is to define water depth through time. Whether it is a deep ocean it was deposited, whether it was uplifted. Again, how deep was water depth? That's something which you need basically to reconstruct from your facies analysis of the sediments and also from the wider context you're working in. At the bottom, you also need to define a temperature history. Here in this group, usually they work with a quite nice boundary conditions, but which is the 1300 degree boundary condition at the asthenosphere boundary. That would be also nice here, but they never included this here. They have provided an additional tool to reconstruct the heat flow. So what they decided to do at some point was to define a heat flow through time, and this can change over time. That you need to construct and reconstruct from your data set and from the environment you're working Temperature top. Then thermal conductivity due to pore-filling fluids. That is done that's done by the project, by the program, depending on what kind of hydrocarbons form through time. So if you run your model without hydrocarbon generation, the result may be at the end a little bit different than when you generate hydrocarbon and form accumulations. But on the large scale of basin studying, this is not a significant point, at least for our question. Okay, paleostructure would be things like mountain building or water depth. And this is just to illustrate this a little bit. That's the interpretation, that's the visualization, how the delta has formed and deposited sediments out into the ocean. If you don't correct for the real water depth, the model would look like this. So all the geometries of the layers would be incorrect. With respect to hydrocarbon migration, basically all the hydrocarbons would move out of the system here, if this would be a source rock down here. So with respect to your exploration target, to get the geometries correct is a very essential problem which you have to solve at some point. So basically, to roll up, simulation is calculation of compaction, of heat flow, fluid flow, and the chemical transformation of the system. And as a function of time, because you're looking at the entire history of the basin, and the additional processes like chemical transformation, they are controlled by the temperature, how it evolves through time, and by the pressure to a certain degree. Quick look at compaction. Compaction changes with depth. The easiest representation is the one which was formulated by Ati many decades ago. The model itself now, they all have formulations which calculate compaction as a function of pressure. You just need a different exponent and different parameters to calculate this correctly. But basically, compaction will always decrease with depth. If you can release the water, or which is squeezed out due to compression of the sediments or compaction of the sediments, then the system is assumed to be in hydrological equilibrium and will follow some kind of a curve like this, depending on the rocks. If you cannot release the water because on top you have a very impermeable layer, the most impermeable layer being salt, then you can build up pressure, you produce overpressure, which at some point, if it is able to break the seal, will either be released instantaneously and then the system will compact, or it may persist and form a drilling risk, or it can also resolve very slowly over time if there's enough time available. These things you can try to model with your model and then give the exploration people some guideline what to expect. Yeah. Collection of compaction curves which are available, and basically they provide the background for the lithologies which are defined in the packages you use and use for calculation of shale porosity or limestone porosity and so on. The main heat transfer process in these packages always is conduction. Convection is really not a significant part in these packages because resolution is inadequate also with respect to time, because conduction is a relatively slow process. You can handle this quite nicely in the project. In the simulation, convection would be a very short-term process which would increase your calculation time significantly, and at least it's not considered to be the most significant process on this scale. Thermal conductivity, just short impression, can vary significantly from relatively low for shales to quite high for pure sandstone, or if you have then quartzite with almost no porosity, it's even can increase even more. Yeah. Thermal conductivity of the solid matter is always relatively high. Coal has a very low conductivity because it's organic material, and the thermal conductivity of water is also quite low. And if you have filling of air or gas, the gas component, it really decreases the average conductivity of your lithologies. Just a few values. Heat production may be interesting because you have radioactive material in the rocks which decay and form heat, adding to the overall heat flow of the or temperature history of the of your section you're looking at. Very dependent on the lithology. At the moment, you don't need to worry about things like this because they are included as default values in the lithologies which you can choose, but would be a parameter one could have a closer look if necessary. A few more terms which come up quite frequently. There are different methods to calculate flow. The nicest one, or physically most correct one, is Darcy flow because it has a physical formulation behind it. But it is quite time consuming to calculate, so it's slow. Ray tracing is a very simple, strong simplification for basically 2D flow on a surface. It's very quick and used for highly permeable layers where they assume that viscosity is not a relevant parameter. And then people came up with invasion percolation. It's an even stronger simplification which just looks at the, I don't remember the English word now, the upwards drive of the fluid. Sorry, I forgot the name, the word. It is buoyancy. Thank you. The buoyancy, and it is something you can optimize extremely. You can parallelize it very nice, so it is very, very fast to calculate. This one is physically most correct, and it's really produces the best results. This one will always focus the flow within a layer. There's little or there's no connection between the upper and the lower layer, so you're always focusing the flow in the layer, which can be nice if you have a sandstone layer between two clay or shale layers, then it's a good assumption. If this is not the case, it can be a pretty bad assumption and provide bad results. Percolation has, due to the buoyancy driving term in it, has a very strong tendency to move fluids upwards through almost everything. So it has also some drawbacks, but it produces very nice and quick results. Calibration data, I mentioned that at the beginning, you need to have something to check your results against. The most common one is vitrinite reflectance. Organic material changes its reflectance depending on the thermal stress it received. Quite simple, if you put a cake in the, or bread in the toaster, if you turn it on too much, it gets dark. Basically, that what happens to the organic material, you deposit it as very immature material in the sediment, you heat it over time, and it gets darker and darker, stronger reflectance, being more mature. That's something you can measure with a microscope quite nicely. And basically, it's a standard procedure. You have to keep in mind that it is always good to have a look at the reports if you have any chance, because it is something which is measured by human beings, by your eye, and people have different eyes, and the measurement is not always reliable. Also, in the reports, you find quite nicely sometimes remarks concerning the problems with the measurements, or also the amount of points they counted. And it is also a statistical method, and it's good to see if they measured only 1 or 2 points, you have to treat the result with much more care when they had the chance to measure 20 points, and also perhaps note it down that some of the data looks maybe not as valuable as others. Temperature data from wells, bottom hole temperature is nice, but if it's not corrected properly, not very helpful. Quite nice temperature data from drill stem tests, because usually they produce really fluid out of the formation and you get quite good results. Apartheid fission track analysis, I'm not going to talk much about this. There's at the university people who have much more knowledge about this topic. Fluid inclusions is something you can measure. Basically information, that's a great idea, on short-term events which were assembled in the cement, in the fluid inclusions by the minerals, and can determine basically short-term events, events, fluid movement through the system. Biomarkers, so you can, there is kinetic for the formation of, and the change of formation of biological components in the system. That is really more complicated and too long for here topic, but it provides information. Stable isotopes, carbon isotopes can be used for calibration. And if you have good kinetic data set of your study area, API and GOR can be used. If you get similar results as they measured at the well site, you have a pretty good assumption that your model also produced the right things. Oh, bitrite reflectance. So this would be some nice vitrinite you can measure. That is a large piece for hydrocarbon exploration. In most of the situation you find much smaller and much less material. The nice thing is there exist models how it evolves through time kinetically. So you can model vitrinite reflectance or calculate the maturity with your model, with your temperature history. The problem with vitrinite reflectance data, you cannot use it to determine inversion events, because the only thing it does, it sums up the thermal stress it lived through. Like a cake, if you cool it, it doesn't get unburned. So when you burn it once, it's over. It will not tell you that it got into cooler regions again. For that, apartheid fission track analysis would be a useful tool. And also it cannot determine a single event. For that, fluid inclusion data can be helpful. And if you are lucky, you get it all from the same site and can make some sense out of the whole thing. Yeah, as I said, there's most commonly used EZRO, not undisputed, but it is the most common approach to calculate vitrinite reflectance over time as a function of temperature. And works quite nicely, not always perfect, but gives you some good results to calculate your model. The results you will see later. Temperature logs can be helpful, but you have to consider the longer the drill, the more deviation you have at the bottom. It's cooler there than it was in nature, and towards the top it is getting too warm because the warm fluid is being pumped up and is heating up the well. Bottom hole temperature, similar problem. The longer you drill, the cooler it gets down there, the less reliable is the data. There are different approaches to calculate corrections. You would need to do this, and drill stem repeated formation test temperatures are usually, if they are available, the best data to work with for your calibration. Okay, apartheid fission track. I refer to Ed Sobel for a nice introduction to that here. And fluid inclusion, I don't know who does that at the university. There are some people here who work on that. Basically what you try to measure is homogenization temperature. You try to reconstruct the composition of the fluid and the gas phase, and from that you determine at what temperature the fluid inclusion was formed, and that if you can also pinpoint down a certain timing when this could have formed, you have basically one step or one point information what happened. Basically, the boundary Triassic, Jurassic get 150 if you have one data point which you could use and see whether your model gets into similar regions. And this is just once more a little summary. You need to set up your model. You need to have a certain concept, what you think the evolution was through time, because there's always a gap somewhere which you have to fill, and that's a good guess, good assumption at the beginning. You have to fill your model with, from the geological side, with real data on the lithology, physical properties and so on. You put it into the simulator, you run it, you look at the result of your model, check it with your calibration data, bit-to-night reflectance data, temperature, appetite, fission track. And then you need to decide whether the result is good for you or whether it's bad. And if it's good, you can start to run different scenarios and see how sensitive and how reliable your data might be. If it's not, you better go back and either look at your physical data you put in, or also at your geological model. You may have forgotten an erosion event, happens quite easily. You may have exaggerated erosion whatsoever. And I think this part, the introduction part, is over here. And now I need to get to one case example to explain you a little bit how we set up such a large model. Just a second. Yes. Okay, yeah, got the right one. So this was a study we've been doing together with the BEG, Bureau of Economic Geology. Don't you want to change a little bit? No? Everything is all right? Okay. On a shale gas project in East Texas, Sabine Uplift area, northwest Louisiana. I'll show you study area, how the model was constructed, boundary conditions, temperature evolution, and then a little bit about overpressure, which is quite significant in this area and therefore important. So you can see down here the Gulf of Mexico. Here is Houston. Over there is Dallas, Fort Worth. And this is the study area. And the white line here in the middle, oh no, we're in the middle of the image, is the boundary between Louisiana and Texas to the west. So you know about where we are. If you look here, you see these little dots all over the place. There are thousands of them. And if you move closer on Google Earth, you see what it was, a drill site. So we have a really nice database to work on. Unfortunately, in this area, they just drill. So they know the area quite well. They have been drilling this area for about 100 years. So the upper part, which is not of interest, if they go deep, they just drill through and they don't collect much samples and not much information. So although we have really thousands of wells to work on, the amount of information is not always that great to construct a model. But we come to that later. The general structure here, the tectonic elements basically are here the East Texas Salt Basin, large salt basin, the North Louisiana Salt Basin. You have this so-called Sabine Uplift area, Sabine Arch. You have several fault zones around here. And then basically the boundary, the Mexia-Tulco fault zone, which is defining the western and the northern boundary of this basin. It basically is a fault rift. It started to rift somewhere around here in the Jurassic. And what else is, this shaded area here is the main area of exploration for shale gas on the Haynesville Shale in this area. And there are so-called Sabine Island complex that are were areas which were high areas at the deposition of the Jurassic source rocks in this area. So in some of the areas, these are either very thin or not existent in this area, in this region. That's why they call them Sabine Island Complex. As input, we had this nice map. It was constructed sometime in the 80s when the Americans were looking for, like in Germany, location to store atomic waste. A lot of money was involved. They produced a very nice map of the top salt in Texas, East Texas Salt Basin. So we had the salt domes mapped quite nicely. Unfortunately, not the same exists for the Louisiana Salt Basin. We had no information in detail and therefore could not use much in this area. So in P12, we tried to construct a nice model of the top salt base, basically the base also of the model. So because all the sediments we're looking at are younger than the salt, than Louisiana salt. And as you can see, the geometries of the salt already gets much more simplified because you cannot really create nice salt domes in petromud. That just doesn't work. It also doesn't like systems where older rise on top of younger sediments of the same layer. That simply doesn't work. So we get these nice cones, but at least we have some kind of salt domes in this area. We got a few not very useful seismic lines, but they show quite nicely that our understanding of the, or our model of the salt has little to do with reality. Reality looks certainly quite different. Another salt structure here. But okay, indication how life may look in reality. Our model is a lot more simplified. We have also all the construction of the seismic lines. In 2D, we have a few indications where the lines are. In 3D, simply had no information, so we had to leave them out in detail. There was documented information on an erosion surface on the Sabine uplift from several wells, and this profile just indicates that erosion took place there over a certain amount of time, and then Austin chalk and the younger sediments were deposited on top of that again. The line, here's a little inset, runs east-west across the border between Texas and Louisiana. So that's about the location. I got from Ursula Hammes some kind of basic information on the lithologies, general structure of the area with ages and so on to set up my model, get age information. We then decide or picked a certain amount of or certain types of picks from the database, which seem to be most relevant for the model, but also most consistent throughout the area. As I said, they do exploration now since about 100 years. That also meant that names change over time, and with very old wells you get a different nomenclature than with very young wells. So we had to find a certain compromise which of the data we would use and which of the horizons were most important. The interest was mainly in the Haynesville shale. Bossier is also exploration area target, but mainly the seal for this area. Some other important horizons were also picked, and as you can also see, the interest of my partner was mainly on the older part, so we have a lot of information here. From the younger part, she provided much less information, therefore the higher you get, the less horizons you have. From the tertiary, I had at the beginning no information. I really had to put this in at a later stage. Okay, a little bit difficult to see here, but you see a lot of red and very little green or yellow points. The color just indicates that the surface, the Paluxy formation, is here not so deep or less deep than at the cooler colors. You see a lot of drill location. Unfortunately, this thing is also a little bit out of focus, I would say, because here it looks much nicer. Sometimes you discover that they drilled along a fault zone. Over here, they follow quite nicely the Mexico-Talco fault line. Some other areas they drilled, obviously, quite a lot along the salt structures. Other areas which were not so of interest have almost no or very little wells. So there's always the problem. In some areas you have a lot of data, can create a relatively nice model. In other areas you have little to no information. The deeper you get, Travis Peak is one of the main formations from which they produced oil, so a huge amount of data is available. So that was still quite nice. But in the deeper areas where it's deeply buried and not of interest for exploration, almost no wells are available. You get deeper, the amount of information starts to decrease significantly. Almost no information from the East Texas salt basin, from the deep parts. There you have a lot of freedom now to construct your model. On top of Sabine, still a relatively good amount of information. Up here, in some areas quite nice, in some areas much too little for the complicated structure that the system is deposited in. And if you go then even deeper, here that looks nicer because the points also include the depth numbers. Matter of fact, the amount of information which is available is decreasing basically by one order of magnitude from one layer to the deeper one, unfortunately. Smack over, which is the deepest part I was looking at in this area, almost no. This area is exploration. It is relatively high up in Arkansas and in Louisiana, so there it's an exploration target. We have some information, but it's not the main area of interest for our model. So with all this information, we started to interpolate the horizons. And that's basically a look at the Travis Peak Formation, constructed on the one hand side from the information which we have from the base of the model, this salt layer and Sabine uplift area, and also from all the well data. And sometimes the result is really quite nice. You see some of the salt domes. The big salt domes here, which were very singular points, were cut out for interpolation because otherwise the model would have to go over very steep gradients which are very difficult to run in. You see quite nicely sometimes are fault zones because they've drilled so much along the fault that you could reconstruct it quite nicely. Also up here. There's another one which runs down here. But the continuation here was somehow we didn't get this properly anymore because there were just not enough wells. So compromise, in general it looks quite nice. In detail it is quite often quite difficult to handle. So we did this with all the horizons we had. That is Haynesville, getting very deep in the central part of the East Texas basin, 3,000 to 4,000 meters, top of Sabine uplift area. Part of it is very densely drilled over the last, now not the last 5 years, probably not anymore, but for the last 10 years for Shakers exploration. But unfortunately, this well data is very difficult to use because most of the wells were deviated, horizontal. And this was information which quite often was missing in the database, exactly where did the deviation and what the real depth is at the end. So we had depth data, but not true vertical depth, and it was not really useful. I must admit at the beginning I didn't realize this problem because I didn't understand what the nomenclature was, and I was wondering why everything shifted in this layer by a few hundred meters all the time, until I realized what my problem was. But at the end we got relatively nice geological model. The colors basically indicate the facies. That is present-day surface. Over there would be somewhere Dallas. Further down here would be Houston. Here you have the boundary between Louisiana on this on the right hand side, and on the left hand side Texas. So that is our geological model. Quite nice, not perfect, but quite useful. Since the lithology is not homogeneous in this area, we had to define different facies distribution. That is something which probably is quite nicely defined for the deeper layers, in which Ursula was working for the last few years. For the younger and the older one, it's not always so perfectly defined, but altogether we should have a quite nice facies distribution for the different layers which we defined in our model. So the greenish colors would be shale, the blue colors are usually some kind of chalk, carbonate, different things given in the different insets here in detail. And the yellowish color is usually sand or sand silt mixtures and so on, as a general tendency. Okay, there's a lot of salt in the system. We do not have a detailed reconstruction how the salt diapirs evolved through time. That does not exist. Nobody spent time on that. For us, we did not have access to the detailed studies they've done in the 80s, so we could only try a very general approach. So basically, that's the nice thing about Petrel. You say calculate the volume of the present-day salt distribution. You get some kind of a volume. The assumption is, at least based to common opinion, salt didn't move on the Sabine uplift area in the highs. There were no salt movements. Present-day salt thickness is almost the same, or is the same as it was when it was deposited. So all the salt which was in the is in the salt diapirs probably is missing from the central part of the East Texas salt basin. So we calculated volume, added some amount because our salt domes are smaller than the reality, and filled up basically our model with salt. Or moved it back to the surface to see whether it still makes some sense when you just look at the layer, whether we don't have very deep pockets or something like this. How that looked quite nicely. So that is our starting condition. That's how it then looks like. In this area, at present day, there is no salt. Probably there never was. In the central part of the basin, it is relatively thick. Maybe it was really a more or less homogeneous layer, but that's beyond the resolution and also beyond the aim of this project. The project was not a reconstruction of the salt movement in the East Texas basin. We just tried to make it relatively a simple approach to at least include it in the model. And then the next step was we have to move the salt again into the salt diapirs. And what we then did is basically cut out of the sediments which are in our model the areas which intercept with the salt domes we constructed, and change the lithology there. The program allows you to, at certain points of time, to switch a lithology which was deposited against another lithology. In our case, we switched it against the salt lithology. So we were able to, from a certain time on, move the salt through the sediment layer almost to the top, depending on how high the salt diapirs would reach. So although this is not correct in all detail, because I don't know the exact timing, and also all the salt diapirs in my model, because I wanted to get finished at some point, move at the same time, which is also 100% not correct, but it's good enough for our model. We could move the salt through time, through the model, and see to a certain degree the thermal effect on that. So this part just shows a little bit better. The pink color is the top of the salt without the diapirs, and the blue are the diapirs. And you can also see we cannot really, it's more like a Lego game. You put cubes on top of one another because it's a rectangular grid. And so if constructing a salt diapir is just putting cubes on top of one another, that it moves through the system. There are compromises, and that's basically part of how do you discretize such a model. It's not perfect reality. We needed to reconstruct the one erosion event, which is documented on the seismic profiles. That is one approach, assuming that it had almost the same thickness over the part where it is missing. No. We have taken the thickness from the part where it exists and basically extrapolated into the area where it was missing. So we altogether get to a relatively homogeneous thickness of the eroded layer. It's an assumption in detail probably also not correct, because in such ideal systems usually don't exist, but for the approach, for the model, it was absolutely sufficient. There's a second erosion event which is not shown here. This is something that's tertiary erosion, which is mainly deducted from vitrinite reflectance data from the brown coal which they're producing in Texas mainly. Not shown here. That is the tool I mentioned before. Surface temperature on the Earth through time. So this is a time scale going back to 360 million years. That is position on the globe, and basically you enter your present day location in the model, then by some kind of nice algorithm, which I don't know, calculates how temperature evolved through time at this point of the Earth. Good enough. There is a relatively well-defined heat flow map of present-day heat flow in the US, and the interesting part is not so much the absolute value, which is also of interest, but that this part of the Sabine uplift area is relatively warm compared to the East Texas Salt Basin. That was basically the part which was quite interesting for us. Try to include this by adding some more crust underneath the model. Didn't work in detail because probably we didn't have the right composition. Basically, at the end, we decided to define two regions of different heat flows, one a little bit lower, the other one a little bit higher, and together with the underlying crust, it produced relatively good results. Basically, we tested three heat flow histories. The one is not shown here because it's just at the beginning a continuous heat flow of 60 milliwatts through time, no change. Then considering this heat flow or the rifting event, and therefore the increased heat flow in the Jurassic, which warmed the entire basin in this area. And since this was not being very successful, or in detail not so successful, we also looked at increase of heat flow during these two inversion events. Whether this is justified or not, still under discussion, but the results look okay. So that is just one barrel history, typical for the Sabine uplift area. So it's Upper Jurassic, very rapid sedimentation. In the Lower Cretaceous, still sedimentation, but not as rapid as in the Jurassic. And then again, very rapid phase at the end of the Lower Cretaceous, the short uplift event. Whether this is a hiatus or whether this was a little bit slower erosion is not quite certain. Then throughout the Upper Cretaceous and the Paleogene, still sedimentation going on, increasing towards the Eocene, and then continuous uplift and erosion until present day. And the overlay show the temperature evolution through time, and blue colors indicate low temperatures, and the red one relatively warm temperatures, also indicating that highest temperatures occurred at maximum burial, probably increased by the heat flow event in this area. But that's something we need to discuss. A little bit more simple, East Texas Salt Basin, because there probably was no erosion event in the Cretaceous. At least it's not documented in the wells we have, and probably only a very limited amount of erosion from the or in Neogene times, to make it short. There's some erosion took place, but very little over in younger times. So that looks more simple than the East Texas Salt Basin. Since we have no calibration data for the East Texas Basin, all this is assumption, or has to remain assumption. We only have temperature data and heat flow data, so for the present day it looks quite okay, but for the rest, for really vitrinite reflectance data is not available, so we really don't know how well or how bad our model is. This is present day surface heat flow. What you see quite nicely is the chimney effect of the salt structures in this area. You also see some effects of fault zones, which in this model are reflected by a little bit different lithologies. They are seen quite nicely, quickly. What is quite nice, that the East Texas Salt Basin has a lower heat flow than the Sabine uplift. That works also with respect to the dimensions, works relatively nice. Not in all detail the same as it is in the reality, but we have certainly a different resolution than people working on different well sites. So this part is quite nice. Temperature map of Haynesville just should indicate what you can extract from such a model. Temperature data from different horizons. Just two wells to show that we are at least close to temperature data which is measured in this area. These little marks here mark the temperature data which was measured. The line are our calculated temperature distribution at present day, so that works relatively nice. We have quite a lot of wells where temperature is much lower, but probably due to production in this area. Otherwise it would be just way too cool. But without appropriate knowledge on how long the well was operated, this data is not very useful. Then you can calculate maturity, which is quite interesting for the people who do hydrocarbon exploration, especially for shale gas, whether they are in the right maturity window. And you see, okay, where it's most deeply buried, it is more mature. Where it is less deeply buried, when you go to the basin boundaries, it certainly is still, forgot to explain the colors, that is the dry gas window, this orange color. The red color is wet gas window, and green is oil window, and dark green is at the beginning of being mature. When you look at the well extracted from the Sabine uplift area, you see that the Haynesville shale, which was main topic of interest for our study, just is at the boundary between dry gas and wet gas window in our model. All the other stuff is younger and different maturity. Okay, we got vitrinite reflectance data, a wild mixture of data, basically not one single continuous well measured, but all kind of different locations, and tried always to collect those data which fits best together to get at least some kind of a vitrinite reflectance profile through the wells. We have some data from surface mines, so brown coal lignite mines in which are produced in this area. we had some data from the Travis Peak Formation, this the upper one here, and then from the Haynesville. And here you already see the problem. You have a very steep gradient through this area, which is, at least to the lithologies which were given to me, it's impossible to model this correctly. So either data set is not very useful, has problems with the measurements. And at some point, at least for some of the wells, I got the reports, and it showed quite clearly that for this one, for the Travis Peak Formation data, obviously they had very little data to measure, and a lot of data or a lot of material which was not really vitrinite but inertinite or semifusinite, which is something you cannot use for vitrinite reflectance measurement because it's not a vitrinite or it's already too highly or oxidized. So that's probably one of the reasons why these values are very high. On the other hand, the data from the Haynesville Formation, they stated by those from which I had the reports that they had the influence of bitumen in the system. So they were not really measuring vitrinite but bitumen reflectance, which produces different results. Usually bitumen is producing at the same maturity lower reflectance values than vitrinite. So at least to a certain degree we could probably move this data, convert it to real vitrinite, a little bit to higher values. But to make a long story short, the blue line was the one we calculated with a constant heat flow, and it is certainly too cold, or there you see it even better, for the surface data. Not enough, simply not enough maturity achieved. The black line is the temperature history with a smaller heat flow event during the first erosion period in the Cretaceous. Produces basically sort of a compromise between the top values and the lower values. The red line is much too high for most of the Haynesville data, although in some areas we get a relatively good result with Travis Peak. But as I said, I consider Travis Peak relatively too high, so that's why it's marked red, being a little bit not the optimum result. A few more wells. There were some gas exploration wells from the tertiary, which we could use some more data down here. Again here, either one of the model is not producing the very best result. So the calibration at the end, at least we agreed that probably this the black line, or this one model, produces the best results for our data sets we have at the moment. Let's see what else we have. The organic material in this area is very deteriorated changed due to temperature. So nobody knows exactly what kind of a kerogen type it was, because it's all burned out. There are two types are being discussed, either kerogen type 2, based on studies a little bit further to the area where it was not so deeply buried, or a more terrestrial rich material, type 2, type 3, combined material. If you take both and look at their thermal evolution, basically they get transformed during this burial phase in the late lower Cretaceous. And if you have a kerogen type 3, basically everything was burned out at that time. Nothing would happen later on. Assuming, or if the assumption is correct that it is a type 3 kerogen type, a certain amount of transformation potential still exists. So It was not all burned out at the very beginning, although again most of the hydrocarbons were transformed at this very fast burial phase in the Lower Cretaceous phase. So a summary to this part before I come to the short introduction to the pressure system. Especially Travis Peak Formation supports this relatively hot model with strong maturation of organic material. But if you look at the reports, first of all, they state that they measured very few points. There was little data, and they had big problems with finding mostly semi-fusinite and inertinite. So they have to be treated really carefully and with a certain amount of suspicion. The Eocene lignites are unfortunately too far up to give a clear indication. They just show that tertiary erosion has taken place and at least 500, 600 meters, in some areas more sediments have been removed in relatively recent times. The maturity values of the Haynesville Formation in general, not all, but mostly are very low. And there you can read in the reports that they measured a lot of bitumen and relatively little vitrinite reflectance data. Another explanation, and bitumen reflectance is considered to be at the same maturity to be lower than vitrinite reflectance data. So there are formulas to correct this to a certain degree. I didn't use them here. Another possibility could be, but this is a highly debated topic, that the overpressure in this area could suppress the maturity of the vitrinite reflectance data. We tried to correct it for that. There is a model you can do this with. It would work, but again, people are, or there is a very strong group which says it does not have an effect on vitrinite reflectance data. Kinetics are temperature dependent, not pressure dependent. So it would be a possibility, but it's not, put it like this, it's not a very accepted one. If we take the lowest Travis Peak vitrinite reflectance data and the highest Haynesville data, we probably pick the most, together with the Eocene lignite data, the most relevant data, and then we can come up with a more or less reasonable calibration of our model. The initial rifting event is nice, but it has no effect on our model because at that time the sediments were very near to the surface and no influence is visible. This is not quite correct. That I was not careful enough. The one heating event in the Cretaceous cannot be deduced easily from vitrinite reflectance data. The heating events are seen in the vitrinite reflectance data. Whether it's actually one or two is something we cannot distinguish because we don't have enough data. Vitrinite reflectance data of the Eocene coal without a heating event is at least difficult to achieve. We would need more additional sediments and erosion, which are also difficult to assume, to justify. And maximum temperature was reached at a maximum burial. That's quite certain. Okay. Overpressure is a big problem in this area for drilling, so they had a very close look at the overpressure distribution in this area. They collected all kinds of data. Haynesville is really very high, and we tried to model this in our model as well, to include this. These curves now are results from one location as an example to show how pressure evolves. The blue curve is normal hydrostatic pressure. So assuming the system is in equilibrium, we can calculate this straightforwardly and calculate the hydrostatic pressure. At the same time, you can calculate electrostatic pressure, which is the red line. But the actual pore pressure is something which depends on the amount of compaction, release of pore fluid and so on. And this yellow line shows the evolution of the pore pressure through time. Basically, I have to start on this side. In the beginning, it is same as the hydrostatic pressure. It increases due to increasing burial and overpressure formation. And ideally, in this area, it should go very close to the hydrostatic pressure. In this curve, it is really just the amount of water which is not released, which then starts to carry a certain amount of the additional load due to sedimentation. Assuming this model, we get about 50% of the overpressure which is measured in several of the wells. So we started to look for additional mechanism which could increase overpressure in this area. And one is the transformation of organic material from kerogen to oil. So oil formation is producing a little bit of volume increase, and if the volume has no space, pressure formation, and then the cracking of oil which was formed at some point to gas. And that's something the model can actually calculate. And then you end up with a new overpressure curve which is higher than the one just to this, which is calculated based on disequilibrium compaction. But at the moment, we certainly don't get to the point where we would like to go to. What you see quite nicely, let's see whether I have, this curve, generation, this is all. No, I'm missing a curve. I'm sorry. But if you remember correctly, during this phase, hydrocarbons were generated. Most of the hydrocarbons were transformed from kerogen to oil and gas, and then afterwards started to being cracked to gas. And that's also the point where this overpressure starts to exceed the compaction-driven over pressure. So in general, the tendency of the model is pointing in the right direction. Quantitatively, we are still not at the point where we would like to be. So probably there are also other mechanisms driving this mechanism, this process. Okay, again, what you see here, this you can also plot the amount of overpressure, which is just generation and cracking dependent, and you see that this is something which occurs in a relatively short time because heating was there, or temperature was quite high. It's a process which ran relatively fast, and this added up to this amount of hydrocarbon pressure. And then over time, we have a certain amount of loss of pressure from the system again, and that's why the curves are then approaching one another again. So from the theoretical part, it works quite nicely. From the practical part, you will see that in some areas we are able to match the measured pressure. In some areas we are still far away. And if you remember the curve I showed you at the beginning, where they have overpressure which is close to geostatic, we are still far away from that. So probably there are other processes running as well, or the resolution of our model is not good enough, or some of the kinetics are not well enough defined. I don't know. So altogether, this 3D model, with a very simplified salt movement, produces at least quite nice result with respect to the temperature and heat flow distribution in the basin.